I think it really depends. I mean, it's so usually if I'm in London at the department, well, so it's kind of a mix of different things, right? So on the one hand, of course, I suppose for me the main part is the research, and then there in London I also have a group. I have several postdoctoral researchers who work with me and PhD students who work with me, and so I would spend some time, discussing with them, some time, working on my own, some time maybe discussing with collaborators on Skype or something. But then, there are also parts of it that are not directly related to research. You have, administrative duties, editorial work for journals, refereeing articles, refereeing research proposals, these kind of things. So that actually also takes time. And then, during term, of course, we have also teaching duties. And so, so this at the moment, last year, I didn't have any teaching duties. Next year, I'm going to teach a graduate course for the PhD and master students. So I suppose then it really depends. I mean, as mathematicians, we're quite flexible, right? So we don't really need, most of the time you need a piece of paper or maybe a laptop. So you can also work from home, you can work in a coffee shop, you can work when you're traveling also. And you also spend some time just thinking on your own. So then, sometimes you have good ideas just, while you're taking a shower or when you're actually, still in bed in the morning or something like that, right? So actually, it's not always that you're sitting in front of a computer, so it can come at any moment also, yeah. Well, okay, so for the sort of direct applications outside of mathematics or outside of academia, I mean, typically with mathematics, it's kind of difficult to predict in advance, right? I mean, so there are many things. You see, one example is, for example, number theory, which is, the study of just integer numbers that we all know, which was considered, of course, always a very pure area of mathematics without any kind of applications. And famously, Hardy, who was a famous English mathematician, he famously said that he's a number theorist because he does not want to have any application to the real world, and by doing number theory he can be sure that there is no application. And nowadays, actually, some of the theorems proved by Hardy or by people working in this area, they are actually used every time you connect to your bank, right? So to actually encrypt communications. The algorithms that you use to encrypt communications, they are based on relatively hard results from number theory. And without these results, society just wouldn't work at all, because you couldn't connect to your bank without somebody else being able to see what you're doing, right? So you would not be able to do a secure connection to your bank. And so all the modern communication, all the modern economy would be completely impossible without this, but it was absolutely impossible to predict at the moment where these results were obtained, because that was a very long time before computers even existed. Now, so the kind of area that I work in, in some sense it's more closely related to physical modeling. So, for example, the kind of equation that I'm looking at, it's used, for example, to model what happens if you take a magnet and you heat it up, right? So a magnet, when it's at normal temperature, room temperature, right? So it has magnetization, and so the magnetization points in a certain direction, right? So you have the North Pole and you have the South Pole. You have the magnetization points from one to the other. But then when you heat it up, at some point, it loses the magnetization, right? So at some point, the magnetization starts to fluctuate, and then after, sufficiently high temperature, like 800 degrees or something like this, it loses completely the magnetization. There's no magnetization anymore in the magnet. And so now, if you're interested in understanding what happens when you're close to this temperature, right? So when you approach the temperature, so there's still some magnetization, but it starts to fluctuate randomly. So it's not just all aligned nicely in one direction. So it starts to go in different directions, and in different areas it points in different directions. And if you want to understand these kind of fluctuations, that's described by the type of equations that I'm studying. But you see, I mean, in mathematics, one nice thing about mathematics is that similar kind of mathematical objects show up in very different areas. So, for example, if you're interested in also modeling turbulence, like if you take a bit of water and you kind of stir it around and you want to understand how water kind of moves around, so that's described by a similar type of equation, even though it's a completely different situation. But yeah, so that's somehow the type of objects that I'm kind of studying. So what happened is that in the last maybe 5 years or so, together with some collaborators, I've developed a theory that gives a meaning to some of these equations. So for some of these equations, it wasn't really clear what the equation means. You can guess an equation that is supposed to describe a system. But then, for example, in one of these equations, in your guess, you have the solution is not just a number or something, so it's actually a function that depends on time and on space, so you have some sort of graph of a function. And the equation that describes this function depends on the slope of the point, right? So whether the slope kind of goes up or down. But now the problem is that the equation is so that this function becomes so irregular that it doesn't actually have a slope at any point, right? So at every point, it oscillates so fast that it points up and down almost simultaneously, right? It goes really, really fast. And so then when you write the equation, it's not clear what the equation means because it involves the slope, but then the solution has no slope, and so it's not clear what the equation is supposed to mean. And so we've developed a quite general theory which gives meaning to quite a large class of these kind of equations, and also shows that if you try to simulate this in a computer, for example, that what you get, it sort of justifies the fact that it's possible to simulate this in a computer, that if you do different types of simulations, you're going to get the same answers, these kind of results. So it gives you, it shows that these solutions are somehow, physically meaningful, that you get the correct kind of solution in some sense.